Welcome to The Explainer. Today, we're doing something a little different. We are going on a safari into the wilds of randomness, to track down the hidden patterns that are secretly shaping our world.
Yeah, it's a super common feeling. But what if I told you that even in all that chaos, there are predictable patterns hiding in plain sight? You know, from flipping a coin to waiting for customer calls, randomness actually follows rules. And by the end of this explainer, you're going to know exactly how to spot them.
So go ahead, grab your binoculars. We're heading to a place I like to call Probability Island. And this place is just teeming with different species of probability. And just like real animals, each one has its own unique behavior, its own specific habitat.
Now, our mission, should you choose to accept it, isn't to get all bogged down in, super complex math. Nope. It's to become expert spotters. We're going to build up our intuition so you can recognize these patterns when you see them out in the real world. You ready? Let's do this. Our safari begins now. Okay, quiet now. Our first sighting. And it's a big one. This is the most common species on the entire island, the binomial distribution. Seriously, if you only learn to spot one of these, make it this one, because it shows up absolutely everywhere. So, what exactly makes a situation binomial? I mean, it's not just any random event. A true binomial experiment, it's a very specific scenario, and it has to follow 4 really strict rules. Think of them like an animal's unique tracks or its field markings. You gotta know what to look for. And here they are, the 4 essential field markings. Number 1, you need a fixed number of trials. Like you're flipping a coin exactly 10 times, not just until you get tired of it. Number 2, there can only be 2 possible outcomes, success or failure, heads or tails, win or lose. That's it. 3, all the trials have to be independent. What happens on one coin flip can't have any effect on the next one. And finally, number 4, the probability of success has to be the exact same for every single trial.
Okay, let's see one in its natural habitat. This example comes straight from our source material. A survey found that 1 out of 5 Americans, that's 20%, say they visited a doctor in any given month. This is a perfect setup for a binomial scenario.
So here's the kind of question the binomial distribution is literally built to answer. Let's say we randomly pick 10 people, okay? So we have our fixed trials, that's 10 people. We have our 2 outcomes, they either went to the doctor or they didn't. And the probability for each person is the same, right? That 20%. So what are the odds that exactly 3 of them went to the doctor last month? And the answer is 0.201, or, to put it simply, about a 20% chance. And that is the magic of this whole thing. Once you spot that a situation is binomial, you can calculate the odds of pretty much any specific outcome. And trust me, this is way more than just a cool party trick. It's how businesses forecast demand. It's how scientists can predict the results of their experiments.
But what happens when the rules change, even just a little bit? Well, here on Probability Island, just like in nature, when the environment changes, you find different but closely related species. Tweak just one of those 4 binomial rules and boom, you get a whole new distribution.
Let's start with rule number 2. Remember how it had to be just 2 outcomes? Well, what if you have more than 2? A simple binomial can't handle that. But its cousin, the multinomial distribution, absolutely can. So think about a survey where the answers aren't just yes or no, but approve, disapprove, or no opinion. That's a job for the multinomial. Okay, let's try tweaking another rule. What happens when the trials are no longer independent of each other? With a binomial setup, you'd have to do your sampling with replacement, meaning you put things back after you pick them. But in the real world, you usually don't do that, right? That's called sampling without replacement. And because you're not putting anything back, the odds change with every single pick. The trials are now dependent. And this is the natural habitat of the hypergeometric distribution. All right, let's totally shift our perspective for a minute. The distributions we've seen so far, they're all about counting the number of successes you get in a certain number of tries. But our next 2 species, they're different. They're all about the waiting game.
So meet the geometric distribution. This one couldn't care less about how many successes you get in total. It's obsessed with just one thing:
How many times do you have to fail before you get that very first success? Here's a fantastic example. Let's say a star soccer player has an incredible 80% chance of scoring on any given shot. The big question is, what's the probability that their first goal of the game doesn't happen until their 5th try? This is a classic waiting game scenario.
I mean, you can almost feel the tension building, can't you? The first attempt, it's a miss. The second, another miss. Third, fourth, miss, miss. And then, finally, on the 5th try, goal! The geometric distribution is what lets us calculate the exact odds of that very specific sequence of events happening.
Okay, but what if you're not just waiting for the first success? What if, say, a salesperson needs to close 3 deals to hit their quota for the week? The negative binomial distribution is what helps us answer that question. Like, what's the probability they have to hear no 10 times before they finally get their 3rd yes? It's still the waiting game, just leveled up for multiple wins. All right, our final species for today is, well, it's a bit of an oddball compared to the others. Meet the Poisson distribution. This one isn't about success/failure trials at all. It's all about counting how many times an event happens over a continuous interval, like an interval of time or space. So, how do you spot a Poisson in the wild? It's actually pretty easy. You listen for one key phrase, on average. You'll hear things like, the average number of calls a help desk gets per hour, or the average number of customers that walk into a store each day. The second you hear that word, average, your brain should immediately think Poisson.
Let's make this real with an example. Imagine a 500-page book has 200 typos scattered throughout. If you do the math, that gives us an average rate of 0.4 errors per page. In the world of stats, this average rate has a special name. It's called lambda. And here's the really cool part. Lambda is the only piece of information the Poisson distribution needs to figure out the probability of finding, say, exactly 3 errors on any given page, or maybe even 0 errors.
Whoa, okay, we have spotted a lot of different species on our safari today. So before we pack up and head back to the mainland, let's put everything together in a handy little field guide. You know, a cheat sheet, so you can remember the key markings of each one.
And here it is, your official Probability Spotters cheat sheet. Let's run through it real quick. Binomial, that's your baseline, right? Fixed trials, 2 outcomes independent. Multinomial, that's just a binomial but for more than 2 outcomes. Hypergeometric, this is your guy when you're sampling without replacement, making the trials dependent. Then you've got the waiting game. Geometric, waiting for the first success. Negative binomial, waiting for the 3rd, 4th, or whatever rth success. And finally, Poisson. Just look for that average number of events over time or space.
So it turns out the world isn't quite as random as it seems, is it? It's literally filled with these incredible hidden patterns. And now you have the field guide to actually see them. So whether you're looking at sports stats or business reports or even just waiting in line for a coffee, keep your eyes open. The only question is, what pattern will you spot first?